In the video 41 of the Foundations of Computational Economics course, we will be looking at the endogenous gridpoint method. This is the best one. This is the fastest and the most accurate solution method. Unfortunately, for some specific problems with continuous choice. So let's see. It covers both finite and infinite horizon cases, although we will be talking about infinite horizon primarily. It is the best way to solve consumption savings problem. But it also is applicable to many other problems, and towards the end of the video we'll talk about the definition for the class of the problems that are solvable with endogenous gridpoint. And because it's so great, there has been many generalizations trying to extend the class of the problems that can be solved by the ideas, by the methods, based on the ideas of the endogenous gridpoint method. So the plan for this video is to cover the theory, and then in the next video we'll implement the endogenous gridpoint method for the consumption savings problems that we've been working on. So EGM is like magic, okay? It's the best. It combines both speed and accuracy when it comes to solving a consumption savings problem or the problems which are similar to them in some respects. So what are the best methods that we've seen so far? Time iterations. That was better than VFI, at least in the k-casing version of the consumption savings problem in the last video. But with both VFI and time iterations, we have to repeatedly solve either an equation, first order conditions, or the optimization problem, and that has to repeat in every point of the state space, right? So every point of wealth, we need to find the optimal consumption or solve the first order conditions for the optimal consumption. Imagine now that EGM is the method that requires no root finding operations. It's just a direct computation. You just compute optimal choices, in one iteration each for different grid points, but no repeated computation of the optimal actions. Well, like I said, only applies to a certain class, and it's kind of hard to grasp. In my experience of explaining the method and teaching the method, it turns out to be, because it's magic, you have to turn your head around it and spend some time with it. So that's what we're going to do in this video. We will use the consumption savings model as the leading example in exactly same form as that we've been using it in this course, with stochastic income and non-stochastic gross returns. But otherwise, the Bellman equation should be very familiar by now. Observe this constraints on the choice of consumption. We will be working as the EGM requires with early equations and focusing a lot on the first order conditions, sort of thinking all the time about the interior solutions, and then only come back to the corner solutions towards the end. But so far it's discrete time, infinite horizon, one continuous choice, the choice of consumption. State space is given by one variable, which denotes wealth, right? And wealth in the beginning of the period. And it is discretized, so we can we have points on some grid over wealth, and income follows log normal distribution. Okay, we've derived in video 39. We've derived the earlier equation for the model, and that's just to remind you, is a combination of the first order conditions that we write for the maximization problem in Bellman and the envelope theorem. We then notice that the right hand side here on both of these equations is exactly the same, and that means that at every time period the marginal value function is exactly equal to the marginal utility computed at the optimal choice of consumption. And then we can plug this fact back into the first order conditions to get the early equation, right? Which essentially requires the marginal utility of the optimal consumption today be equal to the appropriately discounted expected marginal utility of optimal consumption tomorrow, where, the amount of wealth tomorrow results from the optimal consumption today as well. Now, for EGM, we need a new variable. This new variable is going to be denoted A, and this denotes the end of period wealth. Okay, this is wealth after consumption. So the timing of the model is like this: we start the period with some wealth M, then based on the amount of wealth here, we consume optimally, and that gives us this A, which is the money that are left after consumption in current period. And then, of course, this grows. This is exactly the amount that entered the intertemporal budget constraint. So this amount of savings, earns some interest, grows with some gross return, and then we add the income to that amount. So this is just a new notation on one hand. And by the way, when I say savings, you have to be very clear about whether this is a stock or a flow. And of course, just as wealth, this is wealth in the end of the period. It's measuring a flow, right, where consumption is measured in stock. So let's be cautious here about saying savings, which usually means a stock. All right, but I'll sort of slightly misuse the term here and sometimes call A savings. But what it really is the after consumption wealth. Now, let's think about how this variable can, within which interval is it allowed to vary. So if we have the condition on consumption, and A is whatever is left after consumption from M, then naturally A also follows the same limits. It's between 0 and M, although it reaches the limits at opposite situations. When consumption is restricted by M, that means A is 0. Now, why is this important? A turns out to be a variable that summarizes the information about the current period state and choice. Right, so if we know A, we know everything that we need to know about the current period in order to think about the future. The future, the next period wealth, really depends on A rather than on M or C. And this is crucial point for being able to apply the endogenous gridpoint ideas. So we say that A is some like a sufficient statistic for the current period state and choice. And of course, having such a variable in the model is one of the conditions to be able to apply EGM. A is often referred as post-decision state, and this is a term used in operations research routinely. Okay, what does this A give us? Well, first of all, we can rewrite the early equation with A over here. And because this is still an early equation, which is a necessary condition, right? We know that if some function is optimal, some consumption function C of M is optimal, and so is a policy function, then it satisfies this equation where A would be equal the difference between M and C of M. But with the introduction of this intermediate value A, we can also think of this equation now as a way to update a consumption function. So imagine that we're given a consumption function C of M, and then we can plug it into the right-hand side of the early equation here, which is here. And then, think of A as an independent variable now. From the early equation, we can derive the current period optimal consumption, C prime, by inverting the marginal utility. See, this is the marginal utility of consumption today. And because we know the utility function in the analytic form, maybe we also do know the marginal utility function in the analytic form, and we can invert it. And then, calculating this function is going to be just an application of a formula, which is wonderful for computation, right? No iterative solvers or anything like that. Well, of course, being able to do that is another condition to be able to apply EGM efficiently. So we have to have the analytic form of the inverse marginal utility function. And so if we do, then we can invert the whole earlier equation and calculate the C prime, which is the optimal consumption in the current period, given the policy function C of M, and given some values of savings. And then, of course, here's the trick. If we know this C prime, then we can reconstruct the point in the state space where this would be all optimal, right? Where the consumption and savings would satisfy the early equation. And we just add up the savings and consumption, because that's what M is by definition, or rather, that's what A is by definition. That's the difference between M and C, wealth and consumption. And so look at what we have now. Now we can go from a function, some function that tells us, how much to consume for a given value of wealth, M, some policy function C of M, and we can plug it into this inverted early equation, and then we have both C prime and M prime, where primes mean updated, right? We have a new updated policy function C prime of M prime, which is defined in a parameterized way. This is like a parameterized curve where A is a parameter, and we know that A ranges in the interval between 0 and M. For different values of A, we can now derive pairs C prime and M prime, and that defines a function. This is a completely normal, standard, well-defined function. It's just defined using a parameter A in our case. And this is really the importance of this additional variable A that allows us to define this transformation of some policy function C of M to get the C prime of M prime. And if you think back about the time iterations, remember we had the Kalman-Raffet operator that was the K operator, going from the space of policy functions into the space of policy functions, and it would take as an input a policy function C of M and return the updated policy function, where the updating would ensure that the updated policy function satisfies the early equation, right? With the updated one plugged over here, right, and then the old one, the input one, is plugged in one particular place here. Okay, so the Kalman-Raffet operator updated the policy functions. And how did we implement that? We would have a fixed grid over M, and then with the given input function C of M, we would solve the equation for each point on the grid of M. And we would solve for consumption, right? And so we would loop through the points on the grid of M, and we would solve for C corresponding to each of the points on M that satisfies the equation. Solving the equation many, many times, like I said in the beginning, and that's what time iterations required us to do. Now we have a new implementation, EGM-style implementation of the same Kalman-Raffet operator, right? It also takes the input as the function that it goes into the right-hand side, the policy function here. But then instead of using the grid over M, we can fix the grid over A, over the parameter that defines the correspondence here, this curve C of M, or C prime of M prime rather. And now we can go through a grid of A and plug different values here for A and recover the pairs of C prime and M prime, and then combine them into the updated policy function, which I call here C prime of M. Again, primes here means updating. They're not derivatives, so next period. Yeah, I'm not sure I should have used primes all that much. But yeah, so here, this is the updated function, returned policy function. And as you can see, we're just going through a grid of A's, and we're computing this this two quantities. There is no root finding. There are no iterations, which is for every point on the grid of A, we compute these two quantities and combine them together to recognize that they define points in some function, and then we can interpolate that function. And that function is our updated policy function. So EGM can be thought of a much more efficient implementation of the Kalman-Rapid operator, and then the EGM solution is then sort of like time iterations, but with Kalman-Rapid operator being a lot more efficient. So here's the EGM principle. Let me jump to that. Instead of finding the optimal decision in each point of fixed grid over the state space, we find the point in the state space where a guessed decision would be optimal. What does it mean? Before, we had a fixed grid over the state space, over wealth. And for each point that we fixed, up front, for each point on that grid, we would look for the optimal consumption level. Now, instead, with the EGM, now we sort of guess the decision by taking particular value of savings. And of course, savings is also could be thought of as a decision variable, just like consumption. So it's like we're guessing the answer, and then through the inverted Euler equation, we can reconstruct the point in the state space, the amount of wealth, where that guessed action would actually be optimal. Right? Going back to this expression, for each point of A that we can plug into here, we would find the choice that would be optimal for this point of the state space. And optimal in the sense that the Euler equation is satisfied. Right? Just because this is a parameterized version of the Euler equation, essentially. Okay, so these ideas have to sync, but here's the general EGM algorithm. It is time iteration, or it is successive approximating solution in the policy function space. But we set a grid on post-decision state instead of state variable m, in the very beginning. And then we set initial policy like in time iterations, and maybe it's consuming everything. And we can define that very nicely, as I say here, just over 2 points if we use linear interpolation. We can just define it over 2 points, 0 and m bar, which is the upper bound of the problem. And with linear interpolation, we would immediately get this function, right? Now, incrementing the iteration counter I, so that we use I to denote the iterations. And then, for each point aj on this grid of savings, we perform the EGM step that returns the corresponding value of consumption and the endogenous point of wealth. Now, let's look at what this EGM step does. It's over here. But let's do that next. But so this is performed for each point on the post-decision state grid of A. Okay, and then once we've done that, we've recovered a bunch of the CJs and MJs, and we combine all computed endogenous points on the state grid and their corresponding consumption level to build an updated policy function, Ci of m. Now, I is the iteration counter here, right? So by doing this step 4, the EGM step, which is a loop over all points on the grid of A, we are recovering the new policy function, and then we check for convergence. If convergence has not been achieved yet, then we return to step 3, increment the counter, and repeat the same thing. So this is like evaluation of the Kalman-Rapid operator here, but in the EGM way. So how is it done in the EGM way? Here's the sub-algorithm for the EGM step. So this step is performed for each point aj on the grid over the savings over A. So first of all, we compute the next period wealth, right? And this is given by the intertemporal budget. And then, of course, if y is stochastic, then we have to replace y's with quadrature points in order to be able to compute the expectation sometime later. Then for each of these possible points of wealth, we use the previous iteration consumption function to calculate the consumption, or the optimal consumption, it says here, in the next period. And this is done for all quadrature points that we've calculated the next period wealth at. Okay, then we can use the compute the marginal utility for each of the corresponding, for each of the found consumptions, and we can complete the calculation of the expected value, expectation in the right-hand side of the earlier equation. So essentially, we are computing this whole part here. This is the expectation of the marginal utility of the consumption calculated for a bunch of possible incomes, where incomes are replaced by the quadrature points. And then, of course, expectation is just a multiplication with the vector of probabilities of quadrature weights. Okay, then we can use the inverse marginal utility function to compute the optimal consumption Cj in the current period. Right, so we are completing the step by calculating now this expression here. And this is going to give us the Cj, the current period consumption that corresponds to a particular point on the grid of A. All right, and now finally just put together the computed Cj and the point Aj to get the Mj, the point in the state space that corresponds to the point on the grid over A and corresponds to the computed optimal consumption. Oh, this is not very visible. There we are. Now, this grid point, this point Mj, is going to be endogenous in the sense that in different iterations, these points may be all completely different, because this depends really on the consumption function that we've calculated on the previous iteration. And the consumption functions will be updated. And so while the grid over A is not moving, is not changing, the CJs that we compute from the inverted early equation will be changing, and so the MJs will be changing as well. And so on each iteration of the solver, we will have a different grid over the state space. And therefore, this method is called the endogenous grid point method, right? That's because the grid over state space becomes endogenous in a sense that these are the points that correspond to some fixed grid of, optimal choices of savings. And that actually also imposes a bit of a practical issue when we check for convergence over here. Because now we have to compare these two functions, consumption functions calculated at two different iterations, but they are defined over different points of M. So we have to reinterpolate one of these functions to compare to the previous one. But that's all right. That's an additional interpolation task to calculate the error in the convergence. But we can do that. So, what are the properties of the EGM algorithm? Well, it's a successive approximation solver in the policy function space. Let's be clear about that. And it needs to converge in the policy space in order to solve the infinite horizon problem, just as VFI or the time iteration solvers. Now, in the finite horizon problem, it is still doable, right? But we don't need to converge. We just have to compute the policy function for each time period. And therefore, the EGM is completely applicable for the finite horizon problems as well. It's just a simple change of the iterative algorithm in the solver. It has to stop not when it converged, but when it ran out of time periods, essentially. And one other addition is, of course, that all these policy functions now would have time subscript in the finite horizon case. And the solution is a whole collection of functions rather than just one function which is time invariant. All right. Now, so it's the infinite horizon case is solver has the same structure as time iterations with new implementation of the Kalman-Rafford operator. That's what it is, really. Yeah, the difference in the operator is that the policy function is updated with the EGM step rather than equation solver. But the main property of the EGM algorithm is that it doesn't have any iterative root finding operations, be it an optimization problem to solve or an equation for the first order conditions to be solved. And so it's fast. It doesn't repeat work at all, except for the work to compute the optimal choices. And it's just, a few analytical functions evaluated and you get that. But also think about this. We're using early equation to find these endogenous points in the state space. And so in all of these points, the early equation is satisfied exactly. Right? So if we go back to thinking about the measuring of the accuracy of the solution, where we use early residuals to check for the accuracy of the numerical solutions, then at least in the endogenous points, the early residual in the solution produced by EGM is exactly 0. Maybe between these endogenous points, due to interpolation errors, for example, there can be some inaccuracy in the solution. But at the endogenous grid points, the early residual is 0. So this method, because of this, has the highest potential of being very accurate among all of the methods that we have seen so far. And moreover, what objects are we interpolating here? Well, we have to update the policy functions, and so we are interpolating the policy functions. And similar to what I said about the time iterations, because policy functions are, less curvy compared to the value functions, they're more linear. So the interpolation, at least with the linear interpolation, is much more accurate. And therefore, there is good reasons. This is another good reason for the EGM to be very accurate. So it's both accurate and fast. Wonderful. The trade-off that we usually face is no more here. Okay, let's look at how it works in practice using a deterministic consumption savings model. Being deterministic, we don't have any expectation. We will implement EGM for the full stochastic Deaton's model in the next video. But here, let's just get some hands-on experience with how this EGM step works. No expectation, y is fixed. We have the Bellman equation as before. Oh, and also I'm assuming that the utility function is just log. So the marginal utility is going to be 1 over c, and the inverse marginal is going to be 1 over u, right? 1 over the inverse value, essentially. Okay, here's the early equation, and here's the early equation in this parametric form, or rather the Kalman-Rafford operator. Here's some code which this time is written in a very funny way. I wanted to be able to go really iteration after iteration, so there are no loops. But instead, I'm writing every iteration sort of explicitly in different cells. And to make this run correctly, I need to clear the memory of the notebook, and this is done with this additional magic command. Unfortunately, when it clears the memory, it also loses all of the imported packages, so that needs to be done before we import NumPy, Matplotlib, and we'll have to interpolate. Now, here are the fundamentals for the problem. They are beta, r, and y, and observe here that first I'm setting y to equal 0, exactly. So there is no income. This is a cake-eating problem, although the cake is growing a little bit. We can make it not grow. So this is a cake-eating problem. Now m bar and number of grid points, let them be 10 and 5. Here's our utility function, the log. Here's our marginal utility function, and the inverse marginal is actually the same function, but I'll just write it separately here for clarity. Let's fix the grid on the savings on A, and we've talked about what the bounds for A are already. It's 0 and m bar. But the question that you should think about is how do these bounds change if the restrictions on the consumption choice changes in the original problem? And then here's our initial consumption function. And what it says here is that it's just going to be an array of 2 points, 0 and m bar, and 0 and m bar again, and we're consuming everything, and with linear interpolation, this is just going to give us a 45-degree line. Okay, let me run this. And then in the next cell, I'm setting up for plotting, and so I'm creating some figures here, and this fancy piece of code allows us to say color equals next color and iterate through colors, through a sequence of colors that Matplotlib would usually use for plotting. But we're going to be plotting many different objects, so we want to control this iterations of colors. And here I'm going to be plotting different things in the three axes that it created. But let's plot the 0th iteration and talk about the plots and the color, right? The color is blue, the first one. So what are these plots? I want to plot the savings, the post-decision state A, on the horizontal axis in the first two panels, okay? And this is going to be consumption and wealth. So this is the derived Cj, or for different points j, and this is the mj for different points of j. And in the initial iteration, we just start with the consumption function, which is already given. And so here, I'm plotting this curve, the consumption function, which is given in the parametric form. So here I'm going to be combining wealth and consumption that are the verticals here, in wealth and consumption. And like I said, in iteration 0, we just start with 45-degree line. Let's go to iteration 1 and see what happens here. Well, first of all, we will create the interpolation function for which is called policy, using the M0 and C0 grids over the initial policy function, initial consumption function. And then we'll prepare some space for M1 and C1, and this is the consumption and wealth, which will correspond to iteration 1. And then for each point on the fixed grid over A, like, in the description of the EGM step, we will, for each of these points, calculate the next period wealth. I want it to be bounded away from 0, so that's why there is a max here, so that we avoid calculating the logs of 0. But really it is r times aj, which is the point from the grid, plus y. Then we will calculate the optimal consumption at this point. These are just scalars right now. We will vectorize it later on, or when we work with the real model. But so far, it's just a scalar number. Here's the interpolated policy at that number. So this gives us the next period optimal consumption. And now I'm taking the inverse marginal utility of beta times R times marginal utility of this consumption. So I'm implementing the this expression here as prescribed by the EGM. And then finally, we put together the computed value of consumption and the point in the grid space, and we save that in the as the point of the endogenous grid over wealth. And then we plot the iteration. Let's see what happened. So as we go through the grid over A, and remember it has 5 points, 1, 2, 3, 4, and 5. We calculate this this consumption first, and that happens to be, these values. And then we also calculate these values by adding, these levels with the point itself, and we get something like that. And then we can put them as a new consumption function. So here's the one that we started with, and here's the consumption function after one iteration. And this is how you combine this parametrically defined function, right? So here's the parameter A, the two values that we've calculated. But then we can acknowledge that this point and this point create a pair and put it here. This point and this point create a pair and put it on these axes. And this point create a pair and put it here. A pair, I mean, in wealth and consumption. And so wealth and consumption can be plotted on their own scale, on their own panel. And you can see that the next iteration sort of lowered this consumption plot somewhat. And that's what we actually saw in the solutions before. Then iteration 2 is doing the same thing, but now we are interpolating the previously updated consumption function. And then we're doing exactly same steps, but we're producing the new grid C2 and M2. And here's our third. I'm reusing the figures that we already plotted. And therefore we get the lines saved there. And so this green line is our next iteration. And you can see how it sort of lowers down a little bit more. And now look at the fact that this is wealth, right? Now wealth was defined at these points on the previous iteration, but on this iteration, this grid over wealth moved a little bit. And this is a visual illustration to how this endogenous grid works. The grid over wealth moves over between the iterations. It's the grid over the A, over the parameter that is fixed in each iteration. You can see how these points align. And another thing is that, our upper bound is 10. And this first function sort of goes all the way out, and this one goes pretty far out. The upper bound on wealth is 10, but we are using the grid. We're using the grid over savings, which goes all the way up to 10. And of course, the point where it's optimal to save 10 is going to be the value of wealth, which is above 10. And so we are safely constructing this consumption functions way out, above, beyond the upper limit on wealth, and that's what we see, right? This goes all the way to 20 something. If you want to save 10, that means that you have to have wealth above 20 for the optimal decision to save 10 and consume a little bit over 10. Right? But then as we update this consumption function, this upper point sort of moves back, but it will never be below 10, just as I said, because with whatever the consumption function, to be able to optimally save 10, you really have to have more wealth than that. All right, and you shouldn't be too concerned about this consumption functions extending sort of far beyond the upper limit. We can always just sort of chop this graph at the upper bound of our problem and look at this portion. Okay, now let's go back to the corner solutions. So far, we've only used early equations, and as I said in the beginning, this only covers the case of the interior solutions. What about the restrictions for C being between 0 and m, and thus A being between 0 and m as well? Well, because we can translate this restriction into this restriction on A, we can actually account for the restrictions for these limits, for these constraints, by choosing the appropriate grid over A. So if we don't go above m, for example, in savings, that means that we are respecting the restriction that C is above 0. And if we don't go below 0 in A, that means that we are respecting the constraint that C must be below m. Okay? So it's easy to only implement interior solutions with the EGM method. We just have to choose the grid over A appropriately. But now, how do we add corner solutions to complete the solution of the model itself? And let's look at that. Well, first of all, the lower bound, positive consumption, is usually not a problem at all. And that's because if we have a utility function that goes to minus infinity as consumption goes to 0, right, then this constraint is never bounding, really. It's just impossible to get 0 consumption being optimal because we are down to minus infinity in the utility terms. And basically all the functions that we usually work with, like log or CRA utility, satisfy the condition that the utility goes to minus infinity. Now, it could be that bequest utility or something like that is set up in a different way, and then it does require additional consideration. But in the standards, in the basic models, that's usually not a problem. That's unlike the upper bound. What's going on here? Should it be like this? No. It should be like that. Okay. So for the upper bound on consumption, the point where C is exactly equal to M and the upper bound is binding, we know that A must be 0, right? So if we are consuming everything and the upper bound is binding on the consumption, that means that we are saving 0. We're consuming everything, the whole M, and then M minus C is 0. Now there is the proposition which turns out to be extremely useful to deal with the upper bound on consumption in the consumption savings type problem. If the utility function is in this problem is monotone and concave, then the end of period wealth is a non-decreasing function of M. So if we go and increase M, then the implied optimal A is going to be increasing as well. Okay? And because of this monotonicity, it is also true that if we increase A, then M would be increasing as well. Well, it doesn't say if it's non-decreasing, right? So it's not strictly monotonic. So if we increase, it can be flat, right? Let me think about that. So if this is A, and this is M, so it can be flat, but then it has to increase. Or it could increase, then be flat, then increase again. That's what it says, this proposition. And the proof is not very hard. It's actually in the appendix of the paper at QE that is referenced in the end of the slides. But let's think what it gives us. So imagine that we just calculate some endogenous grid point that corresponds to a equals 0. So I want to find the point where we are sort of touching the corner solution. Okay, but because I'm using the early equation to calculate that point, this is going to be the point where the corner solution is exactly the same as the interior solution. So this is where the interior solution and the corner solution sort of touch. Okay, that is going to be the M0. It's easy to calculate, right? Because we just take the our inverted early equation and we plug a equals 0 there, and this is the consumption. But we know that a is 0 here, so it's like a plus to give us this point. We just plug 0 instead of a everywhere, and that's what we have. That's just the consumption of the income that we get tomorrow. Well, evidently, right? Because if we don't get any income and we saved 0, then there's no money tomorrow. And by the way, this is why we didn't have any problems in the numerical example that we just ran. Remember, we had y equals 0 there. Okay, so this m naught is just going to be calculated like so. And now, because of the proposition, we can say that for all m's less than m naught, the end period wealth must be 0. Let's go again to the graph. So the proposition says that if this is A and this is M, and there is some M naught here where we know that A equals 0. Now, A is non-decreasing, so it could not be that A is something positive and then goes down to be 0 at M naught. No, it's impossible. So A must be 0 all the way to M naught, and then it can increase due to the proposition. Right? What does that mean? That means that at all of the points of wealth between 0 and M naught, C is equal to M, so that A can be 0. Wonderful. That's the solution in the corner solution in this constraint region, which is very well defined. It's between 0 and m naught. Well, assuming that wealth is not negative. And this is given by the analytic formula, essentially. Right? So EGM, unlike any methods that use fixed grid over m, is able to pinpoint with high accuracy the point m naught where the credit constraint becomes binding. And this is essentially a credit constraint, right? You cannot borrow to consume more than what you have. Think about any other solution method that puts a fixed grid over M. And I'm trying to draw this grid here. It's very low probability event that you put a grid point exactly where the M naught is. And that's one of the reasons that that time iterations and value function iterations lose accuracy. Remember, we were talking about the Keynes method of simulating a completely flat consumption profile. Well, without pinpointing this m naught value, it's very hard to do that. But EGM is doing exactly that, is calculating the m naught exactly. And therefore, it's much more capable of producing completely flat consumption profiles when they have to be analytically. Remember, when beta r equals 1, and this whole thing unravels. Okay, but what do we have to do to implement this corner solution in the code? Well, let's see. We know that for all the m's less than m naught, consumption has to be just a 45-degree line in the space of m. So essentially, we just need to add one point, one segment, to the solution produced by the EGM for the interior points. Okay, let's see how that is done. And I'm starting again with all the same code. with clearing the memory, and then here the income is going to be 1. All the other fundamentals are the same. Well, 5% return. And let me rerun the code for graphics. And here's the iteration 0, which is exactly the same as before. But here's, and I've written a function here for the iteration. And here's the iteration function. Now that we interpolate and we start creating, or we allocate space for the new updated consumption function, observe here that we are allocating an additional point that we have to add to the solution. And this additional point is just going to be 0, the origin. This is going to be the first point of the solution. And think about that. So we will have some solution, we will have m naught somewhere, and there's going to be consumption. This is consumption. This is m. This is m naught. There will be some level of consumption that corresponds to the m naught, and we actually know that level of consumption. That's also m naught, because this is the point where you consume everything. But this corresponds to a equals 0, and then for higher a's there will be some more points produced by Egm, with consumption function going like that. And now what we have to do is essentially we have to add a 45-degree line, and we're doing that by putting a point here and using linear interpolation. So just one additional point at the origin with linear interpolation will give us the 45-degree line, and then the rest of the points can be produced by Egm. So this is the treatment that will allow us to take care of the corner solution. And so this is what's happening here. And then this is the Egm step as before, except that now we're putting all of the points in sort of in the 1+ index compared to before. And also I've created here the extended A grid, which basically just adds an n in the beginning at the first point. So it's just a grid of n+1 nans, and then we replace everything starting from the second point with the original grid A. And this is for the plots, right? So that we can plot this extended vectors M1 and C1. Okay, and let's run this. This is iteration number 1. And you can see here, this is where the change has taken place. Now the 5 points, 1, 2, 3, 4, 5 points of Egm on the axis A of the parameter, they produce this 1, 2, 3, 4, 5 points in the consumption, where consumption is an interior solution. And then we've added this one little here, and this now is a 45-degree line. See, it coincides with the initial iteration where it is a 45-degree line with the blue line. And this little region here corresponds to the interior solution. If you think about the economic interpretation of this, this is very natural, right? If you have a very little wealth, and you know that tomorrow you're going to get an income of 1, and as a matter of fact, let's try to do it more visible, to make it more visible, and let's say that income is going to be 3, and rerun all of this code. Look, now income is, this point is all the way up here. Because we have a line on 5, let me set it to 5. So income in each time period is 5. So if you have wealth which is less than 5, something didn't work. There we go. So if you have income which is less than 5, and you know that in the next time period you're going to get 5 anyway, then you may just as well consume everything, and then next time period you get 5, right? This what defines this. That's what defines this region where the whole wealth is consumed. And that, of course, cannot happen in the consumption, in the cake eating problem, where if you consume everything today, then you're left with zero consumption tomorrow, and that's minus infinity, as we've seen. Okay, and then, the next iteration, we'll still have that constraint region here and the corresponding kink in the consumption function. Consumption function is continuous, but it has a kink over here at 5. All the rest of EGM works exactly in the same way, right? We go through the grid over A, over the post-decision state, and it goes from 0 all the way to 10 in 5 points. But the 0th point, as you can see, produces 5 on the wealth grid. So if you save 0, then tomorrow's wealth is going to be exactly 5, right? 0 does not earn any income, and then tomorrow's wealth is going to be exactly 5. And then that corresponds to this point here. We can actually do it for many iterations, and you can see that the shape of this consumption, the updated consumption curve, is staying the same. And also remember, the 10 is our upper bound, and every time, as I was saying, the points produced by EGM sort of go above the upper bound in terms of the of wealth grid. And you can start seeing some convergence, right, in all of these graphs. But what we care about, the convergence here, where we would stop the iterative procedure when we've converged to the time invariant consumption function, which becomes a policy function. Okay, so hopefully I've convinced you that EGM is a really, really nice method, but the question is, how big is the class of models which is solvable by EGM? Let's think about what we needed for the EGM to work so far. Finite or infinite horizon, continuous choice, right? So that we can have the early equation. We wanted to have strictly monotone differentiable utility function to be able to take the inverse of its marginal utility, and we needed it to be concave so that the corner solution can be treated in a nice way. So far, we only had one continuous state variable, wealth, and one continuous choice variable, consumption. So that was a very simple, small problem. And we also needed to have a particular structure on the law of motion of state variables, so that we have the intemporal budget constraints, so that we have the savings, the problem, the sufficient statistic for the state and choices in the current time period. Now, occasionally binding borrowing constraints were fine, and also it's possible to add additional state variables, provided that their motion rule only depends on A, but not on M and C. So in adding this additional state variables, we have to maintain the situation that A serves as a sufficient statistic for everything that happens in the current time period. And this is really needed so that we can take the expectation of the next period marginal utility of consumption conditional on A, only knowing A, but not M or C. And so you may think that this is a rather small class, but in fact it involves many important models from micro and macro, so all the growth models or income fluctuation models, they are part of this framework, or buffer stock models. And the fact that you can solve this in an instance, and I didn't show you any runtimes, we'll look at them in the next video, but you can really solve the consumption savings problem with EGM at the blink of an eye. It's a tiny fraction of a second that it takes to solve a completely full-scale large stochastic consumption savings model with this method. And therefore, you can solve many of them. So you can allow for huge heterogeneity of agents, for example, or you could allow for a large equilibrium model, or you can allow for a complicated estimation exercise, just because you can solve an individual consumption savings problem very fast. But because of this really nice method, there's been a lot of research going into how to generalize it, how to generalize these ideas. With the first being in 2007, a combination of endogenous gridpoint method with a more traditional approach. I believe that was value function iterations to increase the dimensionality of the solved problem. And then there is a study of by Ludovic and Sean, which was published pretty late, but it was written at about the same time. Well, it was probably written about 80 years before. It was published on studying how the multidimensional EGM, which requires complicated interpolation, would be slowed down. So yeah, here we're talking about the multidimensional generalizations, and they are hard because irregular grids require a lot more time to be operationalized. So in other words, if we have an irregular grid, endogenous grid in one dimension, that means that we can just use normal interpolation routines. But if irregular grids happens to be in multiple dimensions, then we have to do something that is called Delaunay interpolation or triangulation-based interpolation, which is a lot more costly. That's in the general case. But then there was a couple of letters or a couple of papers like Matthew White here, which developed a specific interpolation scheme that works with irregular multidimensional grids. It's better than the Delaunay triangulation. But it's still hard. And now I had a little paper trying to formulate the conditions of a problem which would be something like a multiple consumption savings problem. Imagine that you have different assets, not only wealth, but for example, health or human capital that you can accumulate and decumulate in the same manner as you decumulate wealth by consuming parts of it. And then this paper here contains the conditions for such a multidimensional problem to be solvable by sort of a very straightforward generalization of EGM to multiple dimensions. Now, other generalizations also looked at the situations where you would have a non-convex problems. And this becomes very hard because the Euler equation cannot be used alone, right? Because it's not a sufficient condition any longer. If you have a non-convex problem, then the Euler equation, hopefully, and it does, stays a necessary condition. But now you have to worry about the additional solutions which are not optimal in the sense of the dynamic optimization. And so there are several papers here by Julia Fella, and we and co-authors contributed to this as well. And then Jeppe and Thomas had written what's probably a most general generalization of EGM to both multiple dimensions, occasionally binding constraints, and non-convexities. But it is computationally intensive. Okay, here are some further learning resources, and I encourage you to look at the original paper by Chris Carroll on EGM itself. It's a short, nice read, and it's really a nice idea that this method is using. There's literature cited in the previous two slides. There's a bunch of citations who are now using this wonderful method in various applications. All right, see you in the next video where we take back to the code and implement EGM for the consumption savings problem in the Deetons class.